Okay, so let's explain this really cool application of Faraday's law as it applies to a rail, a bar that moves along a rail in the presence of a magnetic field. And this is called motive. Motive means we're moving something forward, EMF. Okay, so let's make sure we're clear what we have here. So we have the B field is right there. That's what those X's are indicating. And notice that it's uniform. They're essentially evenly spaced. We have this conductor, the sideways U, and then we have a metal bar, and it's a frictionless surface that is somehow being moved to the right. And we're going to talk about that aspect in a little bit. So we have a complete circuit. We have a loop, a square loop, and as the object moves to the right, you can imagine that it's going to cover more and more area of the magnetic field, so our flux is changing. So we're going to get an EMF. So based on the numbers, in fact, I'm going to do all the solutions with no numbers. It's the numbers you can put in if you want to. But here's what we know. We know something about the velocity. We know something about the strength of the magnetic field. Question A asks, is current produced in a conductor? Yes. And if we were to justify why, because flux phi is increasing. And if it's increasing, there's a voltage, and there's a complete loop, then we have a current. So I'm just going to put flux is increasing. Now, what direction would that current be? So based on what we learned earlier in the previous page, that's Lenz's law. So Lenz's law, we go through a separate process. So first question, is the flux changing? Yes, we've already answered that. Is it increasing? We've already answered that. It is increasing. So now we take our right hand and we place it in a direction that opposes that increase. In other words, we point our right thumb such that it is in opposite direction of the existing magnetic field. So since the existing magnetic field is into the page, we're going to point our thumb out, and you should see your fingers curling in a counterclockwise manner. Okay, so for counterclockwise, I'm just going to put CC, counterclockwise, and draw it on there. And that's going to be important later on. It gives it an interesting effect. So how could we calculate the amount of EMF in terms of the velocity, right? We know the faster it's moving, the faster the flux is changing, the greater the velocity. Well, we can basically just take Faraday's law and change it in terms of these parameters. So let's start with Faraday's law, where we have EMF. I'm going to ignore the negative, because the negative we took care of with the counterclockwise, is N delta phi over T. Now, this is just one loop, so N is 1, but we could keep it in there if we wanted to, if there were multiple loops. So let's look at the phi. So what is phi? Phi, by definition, is the product of BA times the cosine of the angle between the magnetic field and the face of it, and it's 0, or the normal to the face. So I'm just going to ignore the cosine theta part, all over T. And I'm going to make a slight adjustment to this, is what's changing in terms of flux that's changing, what's changing in terms of B and A that's changing the flux. So it's not the B field, that's constant. So it's really change delta A over T, right? That's really where the change in flux is. So B delta A over T. Well, there's no time in here, so we want to get rid of that. And A, we want to be able to calculate given the information. So let me add one more piece of information that is given here, should be given, or it would be important to be given. And that's the length of this sliding bar. Okay, so we'll assume that we know that. Well, it's given down here. Okay, so that's L. Anyway, so I can look at the area, this area right there, as a, right? So this, I'm going to move down here. So this EMF becomes B, and A is a length times a width, if you will, all divided by T. So where the width is from here to here. And that width is changing. So that's really what's changing. That's changing the area. So how do we calculate that width? Well, that would be simply how fast we're moving by how much time we have. So that's BL times velocity times time divided by time. And we see that the time cancel out, and we're left with our equation right there. So the EMF is nothing more than the product of B times L times V. And you could put a cosine theta in there, and you could have an N in there. So if you want a more complete one, N BLV cos theta. But generally in a motive EMF, the theta is going to be 0 anyway. So usually, I'm pretty sure in a reference sample, it's just B times L times V. All right, so you can plug in the numbers for that. So in part C, we ask if the length of the bar is 0.15 and the resistance of the bar is 10 ohms, what is the EMF and what is the current through the bar? Well, we already have the equation for the EMF. It's BLV, so I'm not going to write that again. So let's do the current in terms of the givens. So we know current is going to be, since we have a loop of wire through resistor, we should be thinking Ohm's law. So that's nothing more than EMF divided by resistance. EMF is BLV, so it's BLV all over R. So I'm going to box that as our solution. Again, you can put in numbers. They're really, at this point, trivial. Next question. And before I get to the next question, let's think about this velocity. Why is it moving to the right? Okay, so either something is pulling it to the right and it's going at a constant velocity, or it's just sliding to the right on its own. Right? It's an object in motion, keeps moving, and we're going to assume here it's frictional. So let's take friction out of the equation here. There could be friction, and you could use a Pfaffen equation. Force friction equals mu times the coefficient of friction times the normal force. But if it's frictionless, is just sliding on its own and continuing to slide indefinitely. And I want you to think about that in terms of an energy standpoint. Could this continually slide on its own at a constant speed? If it did, its kinetic energy would stay constant. But as it slides and creates a changing flux, which induces a current in there, that current is going to produce power in the wires, and so there's some energy loss. So how can it maintain a constant kinetic energy if it's creating energy in the wires? It can't. So that means it would have to slow down as it created energy, and that would act as a magnetic brake. In fact, that's how magnetic brakes work. If you've got something rolling along and you encounter a magnetic field that you can somehow create a loop, then that magnetic field will dissipate your energy in the form of electrical energy, and you lose kinetic energy. And it's a really cool way of braking without any contact. So that implies that in order to move it at a constant speed, there's got to be some applied force here. And that applied force, if it's a constant speed, means by the second law, there's got to be some oppositional force that way. And that's where D is. How much force opposes the bar? So where does that oppositional force come from? Well, it doesn't come from friction because we have a frictionless situation. Maybe by now you recognize that this is a magnetic force, a Lorentz force here. So let's break that down why that is. Remember, we have a current moving in a counterclockwise fashion here. So if there's current in this loop going around and around, then that creates its own magnetic field. And the direction of that magnetic field can be found by looking at, I take that back. It does create its own magnetic field, which interacts with the existing magnetic field and gives a sideways force. So let me restate that. If we look at the current, it's going this way, this way, this way, and then this way. So in all four cases, we're cutting across the magnetic field, so each one of those segments feels a sideways force. We can deduce, without going into it, that these two are going to cancel out. They're going to be equal and opposite. This wire is fixed in place, so we really don't care about it. So let's focus on the force that the bar feels, because that's what we're interested in. So this would be a third-hand rule problem. We have the current is moving up, so take your right hand, point it up. Our field is into the board, and notice your right palm should be pointing to the left. So that's the origin of that opposing force that necessitates the applied force that we have to the right. So that's a magnetic force. And how do we calculate the magnetic force? Well, that's Bill. So our magnetic force is B times I times L. Now we can't leave it like that because we've got to put it in terms of our givens, and we were not given current. So we already have a solution of current right there. So that becomes B times BLV over R times L. And so I'm going to write it up here. If I put my terms together, B squared times L squared times V all over R. So that is our force. That's how you'd calculate it based on those given values. And it's kind of cool how there's that self-consistency in that there's a force that opposes that moving thing to conserve energy. All right, what's the power output and the power input? So the power output is electrical. right? By moving that bar, we're creating electrical energy in that quasi-circuit. Our input is coming from mechanical. In other words, that applied force that is making the bar move to the right. So if you think from a conservation of energy standpoint, how should those two compare? Well, hopefully you're saying they're the same because there's no losses due to thermal energy because of friction. So let's prove that they're the same. So our power output, output from an electrical standpoint is our voltage across it times the current. We could do V squared over R, that's probably a lot easier, or we could do I squared R, but I'm going to do the conventional voltage times current. So our voltage we already know is BLV. Our current we know from right here is BLV, so I'm just going to square it divided by R. So I just did that all in one step. So double check that for yourself. Now for the input, that's mechanical. And you've probably forgotten from last year, but power due to mechanical is easily calculated as, don't write anything here. Remember, the definition of power is energy per unit time, or work per unit time. Work is a force times a distance divided by time, and distance divided by time is velocity, so it's really F times V. So this can be calculated F times V. Well, what's our force? Our force is our applied force up here, which we know is equal to our magnetic force. So I could use my magnetic force equation right here, which is B squared L squared V all over R times V, and that becomes BLV squared all over R. And sure enough, these match up. So I really like this problem. It brings together a lot of different physics that we've learned. Okay, so you can do the practice on your own because I'm running out of time. I will give you the answers. Just make sure we're clear on what's going on. So we have a loop of wire right here moving from one magnetic field to another. And what we see is that the magnetic field has simply changed directions. You're given the time that it takes to do that and what the different magnetic field intensities are. You got 100 loops, so don't forget that. And then you've got square coils of certain dimensions. Make sure you convert centimeters to meters before you do anything. So the first question was change in flux, etc., etc. So the answers I'm going to put here, but you should work them out for yourself. So this is negative, so that means we're losing flux, times 10 to the negative 3 Webers. That's that weird unit. Okay, the voltage across there, you should get positive 2.38 volts. The how much energy is dissipated, I guess has, hold on, let me solve that right now. All right, so the energy created, looking at we can't answer it without more information, so let me throw in here. The resistance of that loop is, let's say, 5 ohms. Okay, so we're not looking for power, we're looking for energy. Be clear on that. So if you do that, at least if I did it right, you should have gotten an energy W of around 0.11 joules. Okay, direction of current. All right, that's a Lenz's law problem. Work it out for yourself, and you should come up with counterclockwise. And then when will the current go to 0? Well, let's answer that right now. So pause it, think to yourself, when will the current become 0? So the information you have is transitioning from here to that spot. Okay, so common answers that are not quite right are this: when this leaves the magnetic field completely. Actually, that's not the case. In fact, as it goes from some magnetic field to no magnetic field, there's definitely going to be current. Some might say when it comes to a stop. Well, coming to a stop, as it slows down, the magnetic field goes from something, or I take that back. It will be the same one, but it doesn't have to come to a stop. So imagine we're already fully in the field, right? We've transitioned from one direction to another. So in the next moment, let's say we're right here. And then the next moment, we've shifted a little bit. But the point is, in those shifts, we're still within the same magnetic field. And so the flux isn't changing. So the current goes to 0 when completely in the B field, assuming it's a constant B field, and that's the assumption here. As soon as it starts to leave, in other words, as soon as this edge here starts leaving, then we're going to start decreasing and we're going to get current again. So in a sense, right, we got a certain current counterclockwise, let's say, is negative. We had a negative current as we was transitioning from the from here to here, and then it's 0 for a little bit, and then